So let's look at this displacement time graph, and let me write the title of it. It's a displacement time graph, which means that it tracks an object's position as a function of time. So I'm going to ask a couple of questions about this graph or this object, and in some parts we're going to have to use a little bit of calculus, and some parts we're going to have to use some of the tricks of the math trade that you've learned in previous years. So the first thing I'm going to ask is to read directly off the graph, what is the displacement at 15 seconds? So since this is a displacement time graph, I can just actually find 15 seconds here on my graph and read off how much I've been displaced, or the object is displaced, and the displacement at 15 seconds is 9 meters. So that displacement on a displacement time graph is the easiest way to calculate, is the easiest element to find. So now if I want to find out how fast this object is moving, I'm looking at velocity. And my first question is, what is the average velocity? So that's what this AVE stands for, average velocity in the first 15 seconds. So starting at 0 seconds and going to 15, what's my average velocity? And as soon as you're dealing with velocity from a distance time graph, you need to calculate slope. So I'm going to draw a straight line connecting these two. This is called a secant line, and I am going to find the slope of the secant line. So the slope of the secant line is the average velocity, and it's rise over run, or d2 minus d1 over t2 minus t1. So this point, that it has a coordinate of 15, 9, and this one has a coordinate of 0, 0. So that means my average velocity is 9 minus 0 divided by 15 minus 0, or 9/15. And if I reduce that, it's 3/5, and it would be measured in meters per second, because the displacement is measured in meters and the time is in seconds. So in order to find the average velocity, you take the secant line and you find the slope. There is no calculus involved. For the instantaneous velocity, so how fast is the object moving at exactly 15 seconds, that's when we have to use the slope of the tangent line at that point. And so this is going to be a little bit of eyeballing, especially since it's hard to use a ruler here on this computer, but I'd have to draw. I'm going to do this one in black, since at 15 seconds I'm going to draw a tangent line, so it just touches the black dot and the graph at that point. So this is a little bit of an estimate, and but the process is what is important. So I'm going to draw my tangent line it's quite long. It's not just a little. If I draw it too short like this, then you're going to get more errors in your measurement. So make it nice and long. And now I'm going to find the slope of that black line. So I'm going to find 2 spots on that black line. So here's one, and here's another, and I'm going to find the slope of that. So the slope of the tangent line is the instantaneous velocity at a certain point. And I'm still got slope is still rise over run, so it's d2 minus d1 over t2 minus t1. And in this case, my 1 point here is 16, 17, 18, 18, and 11, I believe. Just right there we go, 11. And this point right here is 11, 5. So that means my slope is 11 minus 5 over 18 minus 11. And 18 minus 11 is 7, and 11 minus 5 is 6, so my slope of my tangent line, which is my instantaneous velocity, is 6/7 meters per second. So to recap, if you're asked for an average, you're looking for the slope of the secant line. If you're asked for an instantaneous value, you're looking for the slope of the tangent line.